In this video, we're going to look at some of the properties of polyprotic acids, which simply mean that an acid has more than one proton. Some of the examples of these polyprotic acids are H2SO4, H3PO4, H2CO3, and H2S, and there are a wide variety of examples of these. These acids always dissociate in a stepwise manner. And we can look at the stepwise fashion in which these polyprotic acids dissociate, and we'll use H3PO4 as an example. H3PO4 is going to be in equilibrium with H plus H2PO4 minus in solution. The Ka for this, which we'll call Ka1, is going to be 7.5 times 10 to the minus 3. The H2PO4 minus charge can then be in equilibrium with H plus in aqueous solution plus HPO4 2 minus ions in solution. The Ka2, or the equilibrium constant for that second proton to fall off, is going to be 6.2 times 10 to the minus 9. If we have HPO4 2 minus in equilibrium with losing the third proton, it's going to give us H plus PO4 3 minus in aqueous solution. The Ka2 for this is going to equal 4.8 times 10 to the minus 11. So here we have each of these K expressions, and we can characterize or write a reaction for this entire reaction. And remember that if we have a multi-step process, we can cancel out all the intermediates, and we can write the overall equilibrium expression, and that's going to be H3PO4 in aqueous solution, which is in equilibrium with 3 H plus ions in solution, plus PO4 3 minus ions in solution. Our K for this is going to be equal to Ka1 times Ka2 times Ka3, and that's going to equal 2.2 times 10 to the minus 22nd. This is very, very, very small, which indicates that our reaction is going to be heavily reactant favored. Okay, the equilibrium lies over to the left. So for a typical weak acid, the Ka1 is typically greater than the Ka2, which is going to be greater than the Ka3. Okay, if this is a diprotic acid, we don't need to look at a Ka3, but the Ka1 is going to be greater than the Ka2. And from this, we can say that it is always easier to remove the first proton. So if you're describing a particular reaction happening, notice what happens here when we go from Ka1 to Ka2 for this particular acid. When we go down here, we see a very large jump. And then when we go from Ka2 to Ka3, there's a smaller jump. So what we can look at here is for the Ka of polyprotic acids, look into the first dissociation as it dictates the equilibrium concentrations. Because if we have a very, very small K, it's going to give us it's going to highly favor the reactants. And those reactants don't go forward very well. So we can just look into the first dissociation constant, which will dictate our equilibrium concentration of our H+, and which will also dictate the pH for a particular solution that has a polyprotic acid.